Now, a physical property of carboxylic acids when you talk about is what happens, what is the acidity and what's the titration curve look like if you have multiple carboxylic acids. So in this case, I have a tricarboxylic acid cyclohexane. Well, there are no strong acids in terms of organic compounds. They're all weak acids, which just means they have a reversibility constant associated with them. So for each carboxylic acid we have a Ka associated with them. Ka1, Ka2, Ka3. Now here I've just kind of arbitrarily put them up on the board. We label them the Ka1 being the strongest acid, or the strongest carboxylic acid, the most acidic one, and then we start working our way down. Now, it may not be easy to see looking at the figure which one it is, but we can actually just measure what's going on. So, why do we have these three Kas? Well, generally speaking, the strongest one is going to deprotonate, and it's going to put enough hydrogen in the solution to keep the other two, or since there are two in this case, to keep the other two as protonated forms. So if we were to run a titration, so if we were to look at pH versus volume of base, we would actually see three weak acid regimes. The first will be a plot that looks like this. So we have our normal weak acid titration with our pKa1 being the first inflection point. Now, as we begin to titrate, we'll see a second and a third inflection curve. And these correspond to pKa2 and pKa3. Now, a few comments about this. First of all, pKa2 and pKa3 may actually be in basic regimes. Even though this is carboxylic acids, this doesn't mean that the second and third deprotonations necessarily happen in acidic conditions. The reason being is that every time we deprotonate a carboxylic acid, we inherently make the molecule negative. So, if this deprotonates, it now has a negative charge. Well, to deprotonate again, now it has two negative charges. Well, there's H pluses in solution, so there is an electrostatic reason why those hydrogens will want to gather around the molecule. It may be, particularly with the third deprotonation step, there may be a lot of energy required in order to separate the hydrogens in solution from the big -3 charge or -2 charge that you see in solution. So that's one thing to keep in mind. The second is that we can create scenarios where there are charges across the molecule. So if we do the first deprotonation, this ends up being a negative charge. We do have to find a point here where, at some point, if we acidify enough, we'll end up making the molecule neutral. So just keep this in mind with multiple carboxylic acids in terms of their behaviors on pH. Traditionally, one of the groups is going to dictate what the pH is. Now, we can successively remove protons and make it more and more negative, but this is going to generally require much more basic conditions. Now, another thing to keep in mind is that our Kas here, the first deprotonation is always the easiest. Second and third get harder and harder simply because we're putting a negative charge in the molecule, which makes it successively harder and harder to remove further H hydrogens plus ones from the molecule.